All right, we're back. We finished our discussion of soil types and some of the definitions and concepts revolving around the soil that will support our pavements. Now it's time to start with a basic rigid pavement design. Remember, rigid pavements are concrete and flexible pavements are asphalt. Asphalt pavements are great for roads, but generally have higher maintenance costs and shorter lifespans, and they are generally not used for commercial or government airfields. What kind of pavement we design will depend greatly on what kind of traffic will be using it. For traffic calculations, we will be using the Pavement Transportation Computer Assisted Structural Engineering software called PCASE, provided by the U.S. Army Engineer Research and Development Center. Don't worry, you won't have to learn or use this little program, at least not as part of this class. Just be aware that nowadays, instead of using tables and charts and manuals and slide rules for pavement design, we've invented robots in the form of computer programs that automatically help us out with our pavement designs. They can cut design time and possible sources of error to a tiny fraction of the old ways. Only the lightest duty, most benign pavements are still designed manually because of the very cumbersome nature of a rigorous design of a heavy-duty pavement using manual methods. We're just going to show you the inputs and outputs of one such typical program that you might use if you were ever to be assigned the task of pavement design. We'll be designing 4 different pavements. One will be for a light traffic road, such as what might be in front of Furl. The second will be for light Air Force traffic based on a standard traffic pattern from the PK software. The third will be for heavy Air Force traffic based again on a PK standard heavy traffic pattern. The fourth will be designed for frost protection. Here are the assumptions made in our pavement design. According to the UFC manual, remember UFC is Unified Facilities Criteria Manual, we should design our pavement for a 25-year lifespan. This is a pretty standard specification. We will be converting our traffic for a variety of vehicles to what is known as an equivalent single axle load, commonly called ESAL, for a controlling vehicle. The controlling vehicle is that which will drive the design. That is, it is considered the vehicle capable of having the greatest impact on pavement wear and distress, with the philosophy that other, perhaps fewer or lighter vehicles will be able to use the pavement and not cause any adverse impact. The reason for converting traffic to a single variable is to simplify the design process and to bring everything back to a single point of reference. Remember that there are many other vehicles which will also use the pavement besides the controlling vehicle. They might be lighter, they might be heavier, there might be many more, there might be less. And they will affect the pavement, but at a different rate and in a different manner than the controlling vehicle. So while not the controlling vehicle, they usually have some influence on a pavement's design. For example, the controlling vehicle might be an 18-wheeler, and we estimate we'll get 100 of them in a day. We might also have passenger vehicles, maybe 10,000 in a day. They are much lighter, but might be traveling at a higher speed. The bean counters who developed this method of boiling all traffic down to a single number have determined that a certain passenger vehicle at a certain weight and a certain speed has the same effect on a pavement as, say, 10% or 1% of the controlling vehicle. In other words, 10 or 100 passenger vehicles counts the same as one 18-wheeler. This is just a hypothetical example. The software has already built into it the various conversion factors. We don't have to do that. I've had to do that, and it's pretty much an all-day ordeal. Getting a robot to do the heavy lifting is much better. This will be our first design for light traffic conditions on a roadway with no frost protection. We will determine the minimum thickness the pavement will need to be based on assumed current traffic loads. The design of pavements based on future traffic predictions is an entire field of study all by itself. This chart is a typical traffic pattern used by PCASE for pavement design. But first, let's talk a little bit more about ESAL, Equivalent Single Axle Load. This term is a mathematical construct that resolves the various vehicles into an equivalent single-axle 18,000-pound load. Clearly, very few vehicles will have any axle with an exact 18,000-pound weight per axle. It might be more, it might be less, it might be with 4 tires or 2, but probably not exactly the same. However, scientists and engineers have figured out a way to convert the weight of a vehicle, maybe with 2 or 3 or more axles of whatever weight and tire configuration, into what it would take to be equal to the 18,000-pound load. In this case, for example, 91,250 passes of a 25,000-pound 2-axle truck is the same for design purposes as 19,538 passes of the theoretical 18,000-pound single-axle load, the ESAL. Do not worry about this process. Like many other topics we've brushed over, it's its own separate field of research. In this first example, this road might be for an access road around an airfield or an approach road to the terminal or something like that. Airplanes or heavy service vehicles would not be on this. We've assumed current traffic loads with no increase over time for the future. Like I said, future traffic predictions are an entire field of study. You've all seen those black rubber hoses crossing roadways, usually hooked into a box, chained to a post or a guardrail. These are traffic counters. They used to be very simple, and each bump measured was counted as an axle passing over that point. A person would be assigned to sit there with a clipboard and take notes about the vehicle mix and estimated speeds. Nowadays, the traffic counters can estimate weight based on how hard the rubber hose is depressed. They can measure speed, they can measure multiple lanes at once, and many other functions. Traffic is measured at various times of the year and from year to year, and that starts the process of forming the opinions on future traffic growth patterns. There's a lot of crystal ball voodoo in traffic predictions, and we're not going to dwell on it anymore today. A couple of terms here. Design life passes. That is the daily passes times 365 days times 25 years. It's just simple arithmetic. In the first line, we assume we'll be getting a single pass of a Bluebird Type C bus every day. Once a day times 365 times 25 years is 9,125 passes. It turns out that even though this bus is not considered the controlling vehicle, its specific load and axle configuration somehow exactly equals 1 ESAL. This does not happen often, and it's just a coincidence for this experiment. We see we have a 2-axle truck at 25,000 pounds with 91,250 design life passes, or 10 trucks a day. The computer program has determined for us that this is equivalent to the same damage to the pavement as 19,538 passes of the ESAL of 18,000 pounds. Similarly, we have light cars and trucks, each at 100 a day, and the computer tells us that even 100 a day, they only cause the same influence on the design process as a single pass of the theoretical 18,000 pound ESAL. Again, don't worry about how the computer sorts this out. Manually, this is an iterative process where an initial pavement cross-section is developed, then we run the various vehicle traffic patterns across it and see where the design process has to be adjusted. Then we modify the design and do it again. The PK software, on the other hand, automates the process and spits out a result in seconds, instead of the hours that even a single cross-section would have taken in the past. The minimum pavement thickness for each vehicle and number of passes is calculated based on the traffic graphs in the following slides. The traffic graphs are dependent on the vehicle weight, and there's probably one that's been developed for the exact vehicle of concern or very close. There are dozens and dozens of traffic graphs in the UFC manual for different vehicles, and if you cannot find your specific vehicle, it is recommended to find the graph reflecting the weight and axle configuration closest to yours. Based on the traffic graphs, the vehicle with the maximum required thickness becomes the controlling vehicle. Manually, you have to figure this out each time. Using the P-Case robot, you get an answer in a couple of seconds. You, as the engineer, just have to check for errors in the inputs, as there isn't much chance for mathematical errors that are the bane of the manual methods. Here's how we use the traffic vehicle graphs from the UFC manual. The red lines on these traffic graphs are just instructional lines included in the UFC manual for using the graphs themselves. Our specific parameters lines are in blue. With the assumption that our concrete's flexural strength is 650 psi and the soil's modulus of reaction is 150 psi per inch, we use a traffic graph to determine the required thickness. Remember, these are assumed values. Start on the left side of the graph with flexural strength and move to the right until you get to the modulus of soil reaction, in this case 150. You then move straight down until you reach the equivalent passes for the vehicle specific to your graph. Ours is 28,666 ESALS. On the initial pass through, we'd run this process first with the Bluebird bus graph and its 9,125 passes, then for the 25,000 pound truck with its 19,538 passes, and again for the cars and trucks. Then we'd pick the result that reflects the thickest pavement, and that becomes the controlling vehicle. We then combine all the various vehicle passes, in this case a total of 28,666 ESAL passes. Finally, we go straight across from there to the right to see our required pavement thickness based on the 28,666 pass ESAL traffic. You see our result is about 6.5 inches. If it had been a little more or a little less, we always round up to the nearest half inch per the requirements of our design manual. For the second design, we'll use a standard load for light Air Force traffic provided by the P-Case software. It is not designed for frost protection. Bear in mind that software such as P-Case gives the operator an option of selecting standard, well-researched traffic patterns, or the user can input custom traffic patterns. For this class, we're just going to pick standard patterns. The standard light traffic pattern we've selected uses C-17s and F-15s. We could also pick standard patterns for other cargo planes and fighter mixes, bombers, tankers, and so on. It's definitely not a one-size-fits-all. There's a lot of room for customizing even within the standard patterns. The design life and equivalent passes calculations are pretty much the same as our previous light road traffic design. Our controlling vehicle in this case is a 68,000 pound F-15C Eagle with 425,417 total equivalent passes after factoring in all traffic loads. The P-Case program knows how to convert wheel loads of the various aircraft to equivalent single axle loads, but they're not using the same 18,000 pound ESAL as what we use for roads. Airfields, taxiways, parking aprons, and the like use different ESALs more appropriate to the type of traffic to which the pavement will be subjected. We'll use this number in the traffic graph to determine our pavement thickness in the next slides. You might note that we are using a traffic graph for a vehicle weighing 67,775 pounds. This is because the UFC manual did not contain the traffic graph for our 68,000 pound F-15C. The P-Case software does have the F-15 built in. With the P-Case software, we don't get to see the intermediate steps like this. All the number crunching occurs behind the scenes without much intervention or observation by us. Robots prefer to work in private, I guess. Anyway, you start out again with your flexural strength on the left side of the graph. Ours is assumed at 650 psi. Then you move to the right until you reach the modulus of subgrade reaction at 150. Next, we draw a line straight down to the controlling vehicle's equivalent passes. Ours is 425,417 passes. Finally, we draw a straight line to the right to determine the required pavement thickness in inches. From this, we've determined that for the light Air Force airfield pavement traffic, we need at least 8.2 inches of pavement. This number is rounded up to 8.5 inches. We always round up to the nearest half inch in larger projects and often up to the nearest inch in smaller projects. Now we're going to take a look at heavy airfield pavements. This design is based on a set of standard loads for heavy Air Force traffic provided by the PK software. Like in previous designs, it is not designed for frost protection. Here for this design, we have an assumed mixed traffic pattern, still containing the C-17s and F-15s, but we've added a really heavy piece of equipment, the 217,000-pound fork truck. Even though it's less than half the weight of a C-17, most of its load is concentrated on the front axle, unlike the C-17, which carries a weight distributed across an extensive array of large tires and axles. This pavement might be for a loading apron where the big cargo planes are parked, then loaded and unloaded by these big fork trucks. A cargo plane would come in and park, then the fork trucks load and unload them, with each operation taking many trips by the loading vehicle. PCASE has determined how these various vehicles compare to the appropriate equivalent axle load used for this design. Again, this is not the previously used 18,000-pound ESAL, but it's a similar concept. Do not worry about how to make this switch. Only know that different pavements, particularly airfield pavements, have different equivalent axle loads used for their designs. We're just trying to bring everything back to a single uniform number from which we can base the design. Roadways typically use the 18,000-pound ESAL, but for airfields, to use a tractor trailer as the design vehicle would not make a lot of sense. That type of vehicle has 4 big tires per axle, each with a maximum load of 4,500 pounds. 4 times 4,500 equals 18,000, and a tire pressure of about 100 psi maximum. Airfields will have traffic with dramatically different loading cases, such as the F-15, which carries most of its weight on the main gear. So one single individual tire will carry 30 to 35,000 pounds or more, with tire pressures of 340 psi. In this case, the controlling vehicle has been determined to have the equivalent axle load, so every pass of it converts directly to an equivalent pass. But more or less the same mixed traffic conversions apply here. We end up with 500,280 equivalent passes of our controlling vehicle, a TYC 850L container truck weighing 217,200 pounds. But now look what happens when we start getting into the really heavy stuff. We go right off the charts. Look what happens when we enter the chart with an assumed concrete flexural strength of 650 psi and a K of 150 psi. If we go straight across from 650 psi, we never intersect the 150 psi line, no matter the pavement thickness. So what do? Up to this point, we have only used the K of the native soil in our prototype designs, 150 psi, with no allowance for compaction, in order to keep the lesson simple. We've seen previously how compaction can increase the strength of the soil dramatically. Remember from about 15 minutes ago how I said, look at 34 inches of compaction and see how we get a K of about 400 psi. We can see here that if we'd used a K of 400 psi, we'd end up with a concrete thickness of about 20 inches, which seems like a lot, but is actually not that crazy for a heavy airfield pavement. This discovery might or might not be our solution, but it does give us an indication on whether or not we could have a solution available. What we have to do now is revisit the entire design from the beginning. Maybe for the application we want, we have to investigate the effects of soil compaction on the K for the design. Maybe we need to increase the concrete strength, or who knows what at this point. What we do know is that at first blush, we don't have a solution, so we have to make another run at it. This is the art part of the art and science of engineering, the careful crafting of a clever, creative, elegant solution to a problem using science, mathematics, and empirical data. So we grab a fresh cup of coffee and go back to the drawing board. One more thing. We always provide at least some amount of soil compaction below any kind of pavement when we build them in the military or for the government. In the civilian world, that may vary, but for the government, at least some degree of soil compaction will occur. In these next couple of slides, we'll take a quick glance at what that looks like. Here we are converting our traffic loads to a single axle load of 18,000 pounds. For the various pavements we've looked at, we can see the need to change from an 18,000 pound axle load to a 68,000 pound axle load, or even a 200,000 pound axle load for the design of a concrete service. In the end, though, we often have to convert back to our old friend, the 18,000 pound ESAL, because that's pretty much a standard unit of measure and is what most measures of compaction use. You can see how 400,000 passes of the 68,000 pound F-15 converts to a ridiculous number of passes for the 18,000 pound ESAL. However, when calculating compaction thickness, we ultimately have to convert back to the 18,000 pound ESAL because that's what most of our design charts use. This number is to determine the required depth of soil compaction, as we see in the next slide. This table shows what the military considers a minimum depth of compaction for the soil under a pavement. It uses equivalent traffic loads, type of soil, type of pavement, and percent compaction. We're working with a rigid pavement and cohesionless soil. The typical percent compaction for a subbase is 95%. By looking at the table, we find that our minimum depth of compaction is 34 inches, measured from the surface of the pavement to the bottom of our zone of construction for a light airfield pavement. If you remember from our first example with 28,000 passes of the controlling vehicle, and then look at the chart, we'd only need 17 inches of compacted soil below the concrete surface. Just note that these depths of compaction have not been rigorously determined for our site-specific soil or the conditions that we have. They are tabular values aggregated from a huge number of construction projects peppered with failures. This is an empirical value that, if used, should provide good results. It's not likely to be an economical solution because it's based off worst case, and our site might not present worst case conditions. What it does do, though, is provide a good first point of departure for an initial design. By using tabular values such as those in the USC manual, an engineer can come up with a quick and halfway decent first guess for a pavement design to determine the feasibility of a proposed use or location. Here's a quick summary of the minimum pavement thickness requirements for our designs. The light road design requires a 6.5 inch pavement. The light Air Force airfield pavement design requires 8.5 inches of pavement. And using our design assumptions without compensating for compaction, we see that heavy Air Force traffic pattern doesn't pencil out, at least not right away. Now we're going to talk briefly about the effects of freezing on pavement design. In soil, we have, obviously, soil particles. We also have air, water, debris, and organic materials. Hopefully, our subgrade below our new pavement doesn't contain trash or organic materials, as they will slowly decay and leave voids, and voids lead to settlement and damage. But there will be air and water. The air we're going to try to drive out by compaction, but we're not going to be able to get rid of the water quite so easily. If there's a lot of water and it freezes solid, it's going to expand, and as it does, it will lift and potentially damage any surface or structure supported by it. What we're going to try to achieve by compaction is to increase the density of the soil and decrease the void ratio, thereby leaving much less space for water to occupy. We also gain the structural advantage of having a denser, stronger material, because dense materials simply cannot be compressed as easily as less dense materials. Think of cake, angel food and fruit cake. You can compress angel food easily between your fingers because it's mostly air. You could use a loaf of fruit cake to hold up your car while changing its tire because it's so dense. Uncompacted soil can have a void ratio that can exceed 100%, meaning half the volume of the soil is air. This void space can also be filled with water. It's the water within the void spaces that causes the problems under freezing conditions. The design freezing index is a means to quantify the overall hazard presented by freezing conditions. It's based on how many hours of the year the air is below freezing. 1 hour at 1 degree below freezing carries a certain value in the design freezing index calculation. 24 hours at 1 degree below freezing is the same as 1 hour at 24 degrees below freezing, and that is known as 1 degree day. All this time and temperature data are aggregated into a single theoretical number of degree days for a particular location, and it is used as part of a frost-protected pavement design. Here are some frost protection design definitions. Frost penetration is how far into the soil frost is anticipated to penetrate under the design freezing index conditions. Oddly enough, loosely compacted soil undergoes far less frost penetration than dense soil because the air in the void spaces tends to act as insulation. Loose soil that would be completely unacceptable for direct placement of pavement might undergo only half the depth of frost penetration as highly compacted, low void ratio soil. If we want all frost penetration into the soil to be confined to the layers of concrete, base, and subbase, we have to calculate and build this thickness of frost-resistant soil. Why this is important is that constructed structural layers of base and subbase end up with far fewer voids, meaning, of course, that frost can penetrate into them, but because the voids are far less, there is much less space for water to occupy. And with less water, there will be less overall heave or expansion as the water freezes. Pavements can tolerate minor amounts of frost heave, and one goal of base preparation is to reduce the potential voids to a low enough point that what voids are left hold little enough water to make freezing and the ensuing frost heave manageable. Design base thickness is what it sounds like. It's how deep we have to prepare the soil layers, both base and subbase, under the pavement to keep frost penetration into the native soil to an acceptable level. Subgrade frost penetration with design base is what it sounds like too. It's how much farther into the subgrade frost will penetrate below the prepared layers of base and subbase. If we keep this to a fairly short distance, say less than a foot, then there's just not a lot of frost heave that can occur. This is a typical design chart prepared by the government by agencies like NOAA, the Corps of Engineers, and others using meteorological observations, extrapolations, and scientific judgments. For the Air Force Academy in Colorado, the design freezing index is 1,000 Fahrenheit degree days. There are also Celsius degree days, which are used in exactly the same manner. Interestingly enough, though, or at least it is to me, is that when we are designing facilities to be constructed on permafrost, we have to design in systems that will keep the soil frozen, because if it thaws out, the soil, which normally carries a very high fraction of organic material and a lot of water, turns into mud and a building will sink into it. At Thule Air Base in Thule, Greenland, about 900 miles from the North Pole, special ducting was built under the floors of hangars to keep the permafrost from thawing. The design system didn't work very well, and the ground thawed. The floors of the hangars sank more than 2 feet, rendering them completely unusable. In the repaired system, an entire refrigeration system with cooling coils built under the concrete slabs had to be designed and installed to keep the ground frozen, solid, and stable. Remember how I said dense soil allows deeper frost penetration? This chart is typical of its type, prepared for a variety of soil densities and water contents. Soil that is very dense could be very dry, perhaps as low as 2%, but soil that is native and not very dense could have quite a bit of moisture in it, since there's a lot of room for air and water. In our example, we're going to assume that we have soil that is 100 pounds per cubic foot with a 20% moisture content. Remember that we said our native soil was 20%? We didn't mention the soil density, but 100 pounds per cubic foot would not be too far off. Using 1,000 degree days and following the blue lines, we see that we end up with frost penetrating into the soil about 40 inches, which is about 3.5 feet. If that much soil were to freeze at the native soil moisture contents, we could end up with quite a bit of frost heave and consequently perhaps significant structural damage to pavements and structures. In this slide, we have a schematic of a typical pavement cross-section. We're going to look at it for a minute to see if we can understand how frost moves through the soil and what happens if we put compacted base material in its way. The term A is the total frost penetration in the native unaltered soil measured from the pavement surface. It is unaffected by pavement thickness. It's only a mathematical construct to find a starting point for further calculations. In our case, it's the 40 inches we just discovered. P is the pavement thickness, say the 6.5 inches we determined in our light-duty roadway pavement design we did a few minutes ago. C is what's known as unbound base. It's merely a term for base, subbase, and subgrade layers that have not been bound together by chemical methods, such as being treated with lime or cement, or by other means by which we turn soil into a cementitious or otherwise solid or semi-solid material. In other words, it's just soil. Maybe compacted, maybe not, but it's what's left over after we subtract our pavement thickness from the total frost penetration depth. B is the thickness of our base and subbase layers, and S is what's left over and is the depth we believe frost will penetrate into the native soil once we've built up our layers of base and subbase. Our combined layers of pavement, base, and subbase act to mitigate the depth of frost penetration, so total frost penetration will be less than what we discovered on that little chart shown on the last slide. Here you can see the frost penetration depth equation. This equation finds the depth of unbound base by subtracting the frost penetration depth we just found by the thickness of our pavement. We assumed water content for our subgrade to be 20% and the water content for our base and subbase to be 5% according to our soil type and our design assumptions. Per the UFC manual for frost protection, base thickness should be at least equal to the thickness of the pavement concrete. Therefore, we use a design base thickness of 6.5 inches as a starting point, but we'll soon see that the minimum recommended base thickness won't be adequate to provide frost protection. We will have to calculate a ratio of water contents between the prepared base and subbase layers and the native soil. Here we will plug in the values for our pavement thickness and frost penetration depth to find that our unbound base for zero frost penetration would be about 34 inches. The fact that it's the same 34 inches we discovered way back when we were talking about compaction is just a coincidence. In other words, this means that if we built a 6.5 inch thick concrete pavement on top of our native soil, theoretically, frost could penetrate almost 34 inches below the bottom of the slab. We will also calculate the moisture ratio between our subgrade and our base by dividing the percentage of water in our subgrade over the percentage of water in our base. Using the assumptions discussed in the previous slide, we get a ratio of 4. According to the UFC manual, if our ratio is greater than 3, we use 3 as our value. Relative to the visual aid on the graphic, what has probably happened here is that there was a leak in the piping associated with this manhole, putting a lot of water into the ground around and under the manhole and its associated main line. As freezing occurred, the steel lid and concrete transmitted the freezing temperatures down deep, causing the water to freeze and push the manhole and part of the main up out of the ground. Here, we will get to the final setup for a frost-protected pavement. Starting from the bottom of the chart at about 34 inches for our base thickness for zero frost penetration, we will move up until we hit our ratio value of 3. Then we move left and right on the rulers to each side of the graph to see that our design base thickness is 19 inches and our subgrade frost penetration is 5 inches. For our light-duty roadway, where we figured we needed 17 inches of compacted base, we would need to place an additional 2 inches of base and subbase to limit any additional frost penetration to 5 inches. Or we could place a total of 7 inches of additional base and subbase. That is the 2 additional inches plus the 5 inches of frost penetration, and there would be no penetration into the frost-susceptible subgrade, thus virtually eliminating any danger of frost heave. If we were to approach our Airfield pavement the same way with the requirement of 34 inches of base and subbase, we've already constructed a sufficient amount of frost-resistant material that frost heave should not be a problem. This approach to design does not mean that we have zero frost penetration beyond the base and subbase layers, only that we will have limited frost penetration. In this case, 5 inches is that amount of penetration, and that amount of frost should not cause significant structural damage. This slide shows the thickness of each layer of the subbase, base, and pavement for frost protection. We have 6.5 inches of pavement. We have 33.5 inches of potential frost penetration with zero base or subbase preparation. And with 19 inches of base and subbase preparation, we have a theoretical frost penetration into the subgrade of 5 inches. We're about done here, so let's run through quickly what we've covered today. We talked about discovering the soil characteristics at your construction site and the various ways it can be done, by using site-specific soil investigations or by using online and published data to estimate soil parameters. We talked about a variety of soil types and what sand, silt, and clay can mean to a site's suitability for construction. We talked about the parts of a pavement's overall structure, which could include concrete, base, subbase, and subgrades, and the strength of the soil, measured by the symbol K, the modulus of subgrade reaction, and we saw the effect compaction has on increasing the value of K. We talked about types of joints and how dowels can be used to hold a pavement together against the abuse of traffic. We investigated a few different pavement designs using tabular data and the outputs of the PK software and discovered how changes in traffic patterns can have a significant impact on pavement thickness and on base course construction. Finally, we spent a few minutes on how frost can damage pavements and ways that we can overcome such damage by thoughtful design of a pavement's supporting layers. Thanks for sitting through this. I know that presentations like this can be hit or miss, but I hope this wasn't too bad. When you have the chance to witness the construction of an actual concrete pavement, to include the excavation, the observation of the soil profiles exposed within it, the process of placing and compacting the base and the subbase, followed ultimately by the forming and placement of the concrete and its appurtenances like the dowels and control joints, I hope that some parts of this lesson will come back to you and present an, oh yeah, moment. Okay, that's it. I hope you have a great Air Force day. Go Air Force, beat Army, beat Navy, and we won't even talk about the Coasties.